Welcome to lecture 6. Today we're going to talk about combinational logic circuits again. We touched on this a little bit on the first week in the course introduction, but today we're going to go into more depth on combinational logic circuits, in particular on the way that we represent these circuits and how we move between the different representations. Okay, so we talked about truth tables before. We're going to kind of review that and talk about a kind of graphical or logic gate version of combinational logic and see how it relates to algebraic equations. Right? In particular, we'll talk about Boolean algebra, talk about using Boolean algebra for simplification, and then if there's time at the end, we'll talk about multi-level logic, NAND and NOR gates, and XOR gate. So let me get into it. So first part is about representations of combinational logic. So let me define combinational logic again in case you missed it before. We can look at it this way. It's a circuit that has some n inputs and possibly n outputs, or m outputs, where we have y sub I for each output is some function of the input, the inputs. In this class, we assume these functions are all Boolean functions, which mean they take on one of two values. Every variable and every function takes on the value of either 0 or 1. Also, we say that y is a function only of x. It means there's no memory in here. There's no other inputs. Everything is defined right here. In programming languages, we call this a pure function, because there's no side effects, there's no state. Right? If you change x, y changes. A combination of x will give you a unique output, y. So as soon as you change x, y will change after a little bit of delay, and we'll be talking about the delay later in the semester. The delay from input to output for any implementation of a combinational logic circuit will depend on the technology. As we said last time, for a given function, it's going to be a little longer delay in FPGAs than it will be in ASICs, right? And that's why FPGAs run at a lower clock speed, ultimately. OK, so that's kind of the definition of combinational logic. Let's look at an example. Here's a simple example. So here's our combinational logic block here. It has two inputs, x and y. And I'm sorry, x0 and x1. It has one output, y. So I have a sort of an English language description of the function here. Output is 1 if either x0 is a 1 or x1 is a 1, but not both. OK, so that kind of describes the function in sort of an English language form. We could describe it, represent it as a truth table, where we enumerate all the output for every input combination. So we look at all possibilities of input combinations and define what the output should be. And this, you should see, matches this. There's a 1 here and here, but a 0 the other places. Right? It turns out there's also a Boolean equation version to represent this function, right, which is here. And we get x0 and not of x1, or not of x0 and of x1. This you can get, in this case, kind of directly from the truth table, because what we're saying is the output is a 1 if that's a 0 and that's a 1, or that's a 1 and that's a 0. And that's pretty much what this statement says here. Now, in this class, it's kind of awkward, or in most design, using and not is kind of verbose. So we use the shorthand. If two variables are next to one another with nothing in between them, we call it and. It's just like multiplication in regular algebra. And if there's an or, we use the plus sign for the or. And then the ampersand there means inversion or not. Sometimes we use a bar over a variable to represent not also. So this is a kind of a more compact form of that. And then we have a gate level representation, which is This same function could be represented as a net list of logic gates connected together. In this case, we have an OR gate, 2 AND gates, and 2 inverters. And it gives us the same function. So these are really 4 different ways to represent the same function. Right? And they each have their use. And we'll be talking about their use and how to convert between these during this lecture. One thing is you'd like to assure yourself that, in fact, all these 3 representations. I'm going to leave this one out. These are the more formal representations here. How would we guarantee that they're all equivalent? And I kind of asked this same question the first week. And the answer was, well, in this case, since there's only 4 possible values that the function can take on, we can do a exhaustive proof. We can prove that this, for every input combination, produces the proper output. The same thing with this. We can plug in values, all the possible values for x0 and x1, and make sure that the function evaluates to the proper result. Right? We can do it, if we did it for all combinations, we call that an exhaustive proof, or perfect induction, I guess, is the other name for the same thing. It gets more complicated for more complicated functions, of course. All right, so that's kind of a background on what we mean by combinational logic. There's no state elements here. It's just one of these. It's going to take on one of these 3 forms for us: truth tables, Boolean equations, or gate level representations without any memory. So I'm going to take a step back for a second. You may be wondering why we call these logic circuits. In fact, we talk about doing logic design, talk about combinational logic circuits. Where does this name come from? It's kind of a funny name. Well, it's all historical. You may have heard of logic, which is, it's a form of reasoning, which was been around for many centuries. There was this 19th century mathematician, George Boole, who developed a mathematical system, or an algebra, involving logic. It was called Boolean algebra because his name was Boole, and he was the one who promoted it. In his system, his algebra, variables took on one of 2 values, either true or false. They were trying to prove things, prove truisms, or prove things that must be false, or prove things that must be true. Right? So his variables were either true or false, and they had an algebra that could describe certain situations, and you could do theorems and prove things. Right? So that was all fine and good, and it had nothing to do with electronics at all until Claude Shannon. And you may have heard of Claude Shannon. He's the father of information theory. He's become very important in wireless communication, where we talk about a Shannon limit, which is how much information you can put over the air. Before he did communications, he had a master's thesis, I think it was at MIT, where he showed how you could map Boolean algebra to digital circuits. Because digital circuits take out one of 2 values. Sometimes we say true or false, but it's usually 0 or 1. Right? So all the same mechanisms and all the same algebra that was developed for this logical reasoning could be used for digital circuits if those circuits took on a value of 0 or 1. And those circuits became known as logic circuits because of this. And the algebra that we use is called Boolean algebra because of Boole and his logical reasoning, his logical algebra. By the way, this is really significant. I mean, we kind of take it, what Shannon did, we take it for granted. But before this sort of way of abstracting circuits as an algebra, there was we had no formal way to describe a circuit. A circuit was its own representation. We couldn't abstract it. Once you can abstract it in a mathematical way, then you can manipulate the equations. And that will have a direct consequence on the circuit. So if you want to make your circuit similar, or your circuit simpler, you could express it in a mathematical way with Boolean equations. Then you could manipulate the Boolean equations, maybe cancel out some terms, and all of a sudden now your circuit got simpler, right? Or your circuit got faster, right? You can do that without playing around in the lab with a breadboard and trying different gate combinations. You could do it on paper and pencil with the equation. So that's a very powerful idea. Or if you wanted to show equivalence, one engineer implemented some circuit one way, another engineer implemented it the other way. And you wanted to show that they're the same under all cases. Well, you could express them both as Boolean equations, reduce one equation to the other, or show the equivalence of the two equations, and then you've proven that these two circuits should function the same. So this ability to abstract and use math is a very powerful idea. And unfortunately, we don't have that formalism for other aspects of digital design. When you bring in state elements, it gets much more complicated, and something as simple as Boolean algebra doesn't work anymore. People have tried temporal logic and other forms of mathematical systems for describing digital systems. None of them have stuck very well. So the one that has stood the test of time is Boolean algebra, but Boolean algebra really only applies to the combinational logic part of circuits. So it's of limited use, and particularly these days, since as designers, we don't worry so much about optimizing at the gate level too much anymore because the logic synthesis tools do most of that for us. And later in the semester, we'll talk about how those tools do that. But so this has taken on less significance except for people that are writing those tools. For designers, you write in Verilog and your circuits get simplified automatically. But it's good for you to understand kind of the background, theoretical background for the way that these algorithms might simplify your circuits. And again, if you ever are faced with designing something simple and you don't want to bother with tools or you don't have access to the tools, we want to teach you how to do some of that by hand here. So you could optimize a circuit if you needed to do it by hand. It might come in handy for a job interview someday. People, and job interviews, if you're interviewing for a hardware job, like to ask you about Boolean equations, about optimization. Okay, so in Boolean algebra, the one we use, and there's multiple Boolean algebras, but the most common one uses and or, and not, right? As the primitive operations, and those, it turns out those primitive operations of the algebra also correspond to physical gates. And this was kind of Shannon's thing. He made a direct connection between the operators in the algebra and the physical implementation of the logic gates. So we had a formula then, or a method to go from equations to hardware. These are and or functions, Boolean functions of two inputs. I just wanted to show you a way to kind of think about all the other functions of two inputs. I asked the question the other day, how many functions of two inputs? And we said it's 2 to the 2 to the 2. There's 16 of them, and here they are. They're all enumerated. It's a truth table that has multiple outputs. It has an output for every possible function of two inputs. Some of them are familiar, like and is here, and or is here. This is the constant function 0. Here's a constant function 1. Here's a constant function x. X and y are the inputs. There's function y. Here's exclusive or, which is the one I showed you a few minutes ago. And then we have some funny functions here that we don't have names for because they're kind of irregular looking. This one is a 1 if and only if x is a 1 and y is a 0. We don't have a common name for those functions, but they exist nonetheless. We could build up a Boolean algebra out of any of these functions, take a couple of these functions. In particular, we know that, well, first of all, look at NAND and NOR. NOR is just OR with an inverted output. You can see that because if you look at these two here, they're just the complement of one another. Here, NAND is just AND with an inverted output. So there's a theorem which you could prove that any Boolean function that can be expressed as a truth table can be expressed using NAND and NOR. Right. So this says if we want to implement logic circuits, we don't really need ands and ors and nots as long as we have NANDs and NORs. Right? And the way you would prove this, and I just sketch it out here, is that we can reduce, if we take a NAND gate and we connect the two inputs together, it functions the same as a NOT. Right? And if we take the NAND gate and invert the output using this NOT, then we have an AND. So we can reduce those down to ANDs and ORs. And we know this theorem holds for ands and ors, so we will have done the proof. Okay. Interesting question is, could we show the same thing for either NAND or NOR alone? Is NAND sufficient and or is NOR sufficient? Right. And maybe that'll be a question for a homework or exam or something someday. It's an interesting question to ask. I think you know the answer. I've already told you that people have built computers out of just a single type of logic gate, out of NANDs. The Cray supercomputer was built with nothing but NAND gates, for instance. Okay, so let's look at the relationship between, we talked about these three different ways of representing combinational logic. There's Boolean, algebra, logic gates, and truth tables. So so there's another theorem here. It says any Boolean function that can be expressed as a truth table can be written as an expression in Boolean algebra using and, or, and not. Okay, so that's an important thing because that's going to tell us if we have a truth table, how could we, there is a way to turn that into a Boolean equation. Right. And we'll talk about how to do that in a little bit. But first I wanted to show you kind of the whole map. So these are the three different representations. We've got truth table, Boolean expressions, and gate representations. Now, it's important to know truth tables are unique because that's really the definition of the function. Boolean expressions, there may be multiple Boolean functions that all evaluate to the same truth table. They're not unique. Some might be more compact with fewer terms or literals and fewer operators. Some may be less compact. Right? And then gate representations, they're not unique either. We've already seen this. There's multiple different ways to implement a given logic function at the gate level. Right? The reason we have these three different representations is that they actually serve kind of different purposes for us. The truth table is kind of the definition of the function. But it's, as we'll see, it's really of limited use except for very simple functions. The Boolean expression is very convenient for manipulation because we can use our intuition and our rules about algebra to manipulate the expressions. And then gate level representation, this is close to the implementation because we may have gates in our standard cell library. So if we have a gate level representation of a function, we know exactly how to implement it on the chip. Or likewise inside an FPGA by partitioning it into LUTs. So this is good for gate level stuff's good for implementation, Boolean expression's good for manipulation, and the truth table is the definition of the function. All right, so how do we convert from one to the other? It seems like it would be a good thing to know how to do. Well, some of this is easy. Some of these, so I've drawn all these links. So there's 6 links here moving from one bubble to the other. All right. Going from Boolean expressions to a truth table, that should be easy because you can just enumerate all the different possibilities into the Boolean expression, and that will tell you all values are for what the values are for the function at each row in the truth table. Right. Likewise, for gate level representation going to a truth table, we discussed this previously, you can basically just simulate it, try all input combinations, and evaluate it at all outputs, possible output values. Going between gate level and Boolean expressions is easy also because you look at the operators in the Boolean expression, it's either going to be and or an or a not. Each operator represents a gate, right? So you can just make some collection of gates that directly implements that expression. If you have an and of 2, if you have the or of 2 and terms, each and term represents an and gate, and then the or represents an or gate, and you just wire the outputs of the ands into the input of the or. So, and going back and forth here is easy. So the hard part really is how do you go from truth table to a Boolean expression? Right? Or how do you go from truth table to a gate level representation? Usually the way we do it is we go from truth table to Boolean expression. Once we have the Boolean expression, then we can form the gate level representation. So it all boils down to this one question mark here. How do we go from a truth table to a Boolean expression? And we'll talk about that in a few minutes. Before I do that, I want to give you another example of a combinational logic block. And here is a 4-bit adder. And this is a place where decomposition becomes important. And I'll tell you what I mean by decomposition in a minute. We looked at a truth table for a 2-bit adder the first week in the introduction. And we said that one had two 2-bit variables as inputs. Therefore, it had 4 total bits as input. And the truth table then would have 2 to the 16 different rows in it, because that function could only take on 16 different values. It's more complicated here because we have 2 4-bit inputs. So the number of rows in the table is going to be 2 to the 8, or 2 to the 4 plus 4. So it's 256 rows in this table. Somewhat manageable. It'd be hard to write it on one piece of paper, but you could if you had to. And then there's 5 output columns because there's one function for each of the bits of the output of this adder. In general, there's 2 to the n rows for n inputs, of course. So if n is much larger than 8, it becomes pretty impractical to use the truth table for anything. Right? So usually for complicated functions, such as this, we will decompose it into smaller functions and kind of hook those together. Right? So that's kind of my question at the bottom. Is there a more efficient or compact way to specify this function, the function being the arithmetic addition of 2 numbers? And in this case, there's a very structured way to do addition. Right? We know how to solve this problem, how to represent this function, how to write expressions for it, and how to build it into logic, because there's a regular structure here that we can exploit because we know how longhand addition works. We're kind of motivated by what we do when we add 2 numbers, the way we learned how to add 2 numbers when we were in elementary school. We learned it for decimal numbers, but it works perfectly well. For binary numbers, where you add A0 to B0, you get R0 and possibly a carry. If you get a carry, you bring it over, and then you add this column and get a result. Then you add that column, get a result. Then you add that column, get a result. Right? So we kind of do it working from right to left. It's the standard longhand addition algorithm. And that tells us how we can break this up into adders of columns. Each piece of our circuit takes care of one column, and then they're strung together with this carry. Right? So that really gives rise to this idea of the ripple carry adder. We don't have to do it this way. I mean, if you went back, you could use this truth table, and using the methods I show you, you could write down a Boolean function that gives you these result bits directly without this rippling. And we'll delve into that a little later in the semester when we talk about how to build adders that go faster. Right? Because as we know, there's no unique solution. If you want to ask the question for this truth table, what is the circuit that implements it? There is no single solution. There's lots of different solutions. So if we went directly from here, we get one solution. I'm just showing you a way to kind of factor it into pieces that makes it more manageable. And it comes with consequences. OK, so that's the idea. So then what we do is we can break down what we need to do for column 0 and into a truth table here. And then we can break down what we need to do for the other columns. The other columns are more complicated because the other columns might get a carry in from the previous column as part of it. So here we have to add 3 bits together, get a result bit and a potential carry out. So what I did is just fill in the truth tables here. You could do this for yourself. It's pretty simple. You can see if you add, for instance, this combination of A is 1 and B is a 1, then the result is going to be a 0, but we'll get a carry that goes to the next stage. So I think this is all correct. Now, I've done this enough times. I know that what the functions are in Boolean, as Boolean expressions that represent the R function and the carry out function here. Right? So we know that R is just the exclusive OR of A, B, and C. Right? And carry out is the majority of A, B, and C, which is A times B plus A times C, or B times, or plus B times C. That may not be obvious to you the first time you look at this, but the exclusive OR one is easy to see because you just look here. It's kind of the parity. When you do the exclusive OR of more than two things, it's really a parity function. It says, it tells you what the parity. Here the parity is 0. Here the parity is 1. Parity is 1. Parity is 0. Right? It says whether or not you have an even number of ones or an odd number of ones. That's what parity is. Okay, so then once we have that, we can then build our adder this way, where we just string together these cells, where each cell has inside some implementation of these two logic functions. Now, just to kind of drive home what I've been saying all along is that these set of equations are not unique for those functions. There's other ways to compute carry out, for instance. Here's another form. And this form is alternative implementation using only two input gates. Right? You can think of that as here, what we did is factor out C in. Right? And factoring out like that introduces another AND gate here at this point. Right? But it gives us a way to implement that function with only two input gates. This one is a 3-input gate here, which we may not like. I don't know. Maybe your library only has 2 input gates, and you need to find a way to implement it that way. Right? But the main point here is that there's variations on these equations, and some may be better or worse depending on your implementation technology. Likewise here for exclusive OR, there's a 3-input exclusive OR. You can implement that with a cascade of two input XORs, as shown there. Okay, so now we're going to introduce Boolean algebra. You've probably seen this at one point or another. So a Boolean algebra, this is kind of the formal definition. It's a set of elements B and two binary operators. Binary operator means these are operators that take 2 inputs, generate 1 output. A unary operator, which we are designating with a prime, with a what is this thing called? Quote mark. I don't know, whatever that symbol is called. What's that symbol called? Apostrophe, thank you. Such that the following axioms hold. Okay, so these are the axioms of Boolean algebra. These are the truths that these things are true by definition. Right? It contains 2 elements, A and B, such that A is not equal to B. There's closure, and what closure says is if A and small b are in big B, then A plus B is in big B, and A times B is in big B, and A prime is also in big B. There's commutative laws, and you remember so the nice thing about Boolean algebra is that you can draw on all your intuition from high school algebra, and algebra we learned on real numbers, and it almost always applies, right? So you learned about commutative laws, which means you can switch the literals. By the way, we call these things literals. It's a Boolean variable or its complement. So we can switch the order of the literals, and it doesn't change the value. There's identities. Right? There's a plus and or in identity, which is 0. There's a and in identity, which is a 1. There's distributive laws, just like in regular algebra. And there's complements, right? And we define the complement this way. Okay, so if we let the 2 elements of the Boolean algebra be 0 and 1, and let the plus be or and the times be and the ampersand be a not, then we have a valid Boolean algebra, and we have the one that we are most familiar with. Okay. Now, so this is kind of a given. This goes all the way back to Boole and his mathematical systems. based on these axioms, there's a set of theorems, or true, you could call them laws of Boolean algebra. These are expressions that are known to be true. Right? And we can prove these either by exhaustive proof, or we can prove them using the axioms. Right? Before we look at these, there's this interesting property. There's a symmetry in Boolean algebra. There's a duality property, which it says if something is true for a Boolean expression, it's also true for its dual. And what the dual is you interchange the ors and the ands, and interchange the zeros and the ones that might appear in the expressions. And the literals are left unchanged. That's what I denote here. Right? So the dual of this thing looks like this. The literals all keep the same. The 0 is replaced by 1s. The 1s are replaced by 0s. And then you switch the ands and the ors. Okay. So because of the symmetry, we get a whole bunch of stuff for free. We have theorems, but they're dual also. If you prove a theorem to be true, then its dual is also true. Okay, so these are the things, these are the parts of Boolean algebra we really care about, because these are the ones we're going to use to prove things, or to simplify expressions, or to prove that two expressions are the same. Right? So we have the operations on 0, and some of these just are also the axioms, as it turns out, but some are kind of built up to beyond the axioms. So we have the operations on 0 and 1. We have this idempotent law, which is kind of interesting. It says x or x is x. Right? If you think about that, if you or a variable with itself, you get the variable back. Right? And you can prove this. You could try this for all values of x. 0 or 0 is 0. 1 or 1 is 1. Right? So likewise, its dual form is here, that x and x is x. The involution law is just if you complement something twice, you get the variable back. Right? That makes a lot of sense. It's intuitive. And they have the laws of complements here, and commutative law, as we discussed in the axiom. There's more on this page. These go on. People have proven all kinds of laws, right? I just gave you my favorite ones here. The associative laws, which is kind of interesting. It says we can, if we're doing a set of operations, reducing it down to a single value, the order that we do the reductions doesn't matter. Okay? We could put together x and y first and then put z in, or we could put together y and z first and then put x in. Right? And by putting together, I mean anding or oring. Right? The order that we do it doesn't matter. Right? And then there's the distributed law. So this looks like normal distribution of multiplication over addition. Right? X times y plus, or x times this quantity y plus z is the same as x times y plus x times z. But because of the duality, we also get this one, which might look a little strange. Right? There's distribution of plus over times. Right? And that doesn't work in normal high school algebra on real numbers. Right? Probably the most important ones are the next ones. So if you haven't been paying attention for the last 10 minutes, this is a good time. It's the simplification theorems, because those are the ones that we can actually use to simplify expressions, and De Morgan's law. So first, simplification. This one is probably the most important one. It says x times y plus x times y prime equals x. Right? And we're going to talk much more about that later today, but that's a very powerful one. And I'll show you some examples of using that. And then we'll have the dual version of that over here, where we have it using, instead of being the sum of two products, we have the product of two sums. There's this one here, which is interesting. X plus xy is equal to x. And then this one, x plus x prime y is equal to x plus y. So I'm not going to prove these for you. It's kind of tedious, but it's not hard because there's only two variables and you can prove it with 4 steps by perfect induction. And then there's De Morgan's law. I'll say more about that in a few minutes, but it says that if you have the or of a bunch of literals, if you take the complement of that, it's the same as taking the and of the complemented literals. So you take the complement and you can move it inside, but in the process of moving it inside, you have to change that operation, in this case from an or to an and. And likewise, the dual is over here. You move the prime, the complement in. You can complement each variable, but if to retain the equivalence, then you have to change the and into an or. Here's De Morgan's law again in kind of a graphical form because it relates, the reason it's important to us is relates to the relationship between and or and NAND and NOR. As we will see when we talk about circuits, NAND gates are much preferred over AND gates in CMOS. In fact, NAND gates are preferred over everything. NANDs are preferred over ANDs and ORs and even NOR gates. Right? So being able to convert things into NAND gates is one of the things that we need to do in order to make efficient CMOS circuits. It's because we can make NAND gates with fewer transistors than we can make AND gates. So kind of De Morgan's law gives us a way to kind of do this conversion between gate types. And I like to think of it this way, that if you have a NOR gate, it's equivalent to an AND gate that has inverted inputs. Right? Likewise, a OR gate with inverted inputs is equivalent to a NAND gate. And that's really all, that's just another way to imagine De Morgan's law. And I've proved all that over here for you, so you can kind of see how that exhaustive proof works. OK, so we're back to this one again. So we were asking the question, I said it all kind of boils down to, if we want Boolean expressions and we have a truth table, how do we get there from here? Okay. And the way we get there is using something called canonical forms. Okay. What a canonical form is, canonical means kind of standard. So this is a standard form for a Boolean expression. I said that there is no unique Boolean expression for a truth table, but there is a unique canonical form. Well, almost. There's the dual also. So we actually have two unique Boolean expressions for every truth table. Right? But there's the two unique ones are the canonical ones. There's two types. There's sum of products and products of sums. So we'll look at the sum of products one on this chart here. Sometimes this is called disjunctive normal form or min-term expansion. They all mean the same thing. Right? We define a min-term. A min-term is a Boolean term where there's one that represents each row of the truth table. So here in this truth table, we're saying for this row, A is 0, B is 0, and C is 0. We can represent that algebraically with this expression A bar, B bar, C bar, because this expression is a 1 if A is 0, B is a 0, and C is a 0. Right? So each midterm will be a 1 corresponding to each row of the truth table. So then we can write a Boolean expression that enumerates all the ways that this function f could take on the value of 1. And that's the sum of products form. And there's an example here. It's really going to be just the or of some of the min terms, because this function can take on a 1 if this is a 1, or 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 if this is a 1. And it turns out in the canonical form, only one of those terms would be a 1 at any one time. Right? So what I did is just enumerate all the places where this function is a 1. And so that's that min term, or that min term, or that one, or that one, or that one is a way to express this function. So And then just to illustrate the point, I did it for f bar. F bar is just the complement of f. So we complement the zeros are turn into ones and the ones turn into zeros. And we could express this function f prime as is just the OR of these three midterms here that represent the first three rows of the table. So I had this question here at the bottom. What is the cost? And I put this here because when we think about doing design, we always want to keep cost in mind, because one of the things we want to do is understand the cost of some particular implementation. So this would be an implementation of this logic function, right? So we might want to ask ourselves, is it acceptable? Is it acceptable cost? You would expect that the costs have something to do with how much stuff is in the equation, right? Because all this stuff here, each term represents an AND gate here. In fact, if you did a simple direct implementation of this canonical form, you'd have a 3-input AND gate for each min term. You may have some inverters to invert those variables. And then you would have a 1, 2, 3, 4, 5 input OR gate also. Right? So we should be able to get some estimate of the cost by counting how many gates and how big the gates are. And I'll tell you, in CMOS, it's pretty simple. Roughly speaking, each literal here, which is going into a gate, will require 2 transistors. Right? So if we know that, if this is an AND gate that has, and just forget about the inversions for a second, because what we can do is we can take the 3 inputs and we can make inverted versions of them. So worst case, we're going to add 3 inverters to the whole thing. But just looking at the AND and OR gates, if this is a 3-input AND gate, we can say roughly it's going to cost 6 transistors, right? And we have 6 times whatever that 1, 2, 3, 4, 5 here. So that's 30 transistors there. Plus you have a big OR gate. This is going to have 1, 2, 3, 4, 5 inputs. So there's 10 more transistors there. So roughly 40 transistors to implement this. Now, this isn't exactly true because we would probably not implement it as AND OR. We're going to convert it to NAND or NAND NOR. But the transistor count is sort of accurate, like I said, roughly 2 transistors for each input to a gate. So that will give us a way to quickly estimate the cost of this. More on that later. Interestingly, the function f bar is a simpler function than the function f. So if we really cared about cost, we could implement this function and then just put an inverter at the output, invert the result, and you get a cheaper way to get f. Right. All right, so that's, now, the thing about canonical forms, is that they are unique, but they're usually not minimal. Right? For example, this one, f here, I just copied over from the other page. We can reduce that by using the laws, or these theorems of Boolean algebra that I showed you. This was one. I was on a couple slides ago. So we can apply that here, where we let x be, let me take a second. X is a, b, no. Yeah, x is a, b bar. So we have x, y bar plus x, y. That's going to reduce down to x, which is a, b bar. And then here's another, we can find another place to apply this where x is a, b, and y is c. So we apply that twice. We bring it down to this point. Then we can apply this theorem, which I had, and that will reduce it even further, where we simplify this one down to this one, and then once again down to here. So by applying the laws of Boolean algebra, we're able to simplify f down to something that should be a lot cheaper to implement. Now, this is going to be an OR gate with 2 inputs and an AND gate with 2 inputs, and that's it. So like down to 4 transistors. Not 4, 8 transistors. Likewise, we can do a similar reduction for f prime. And I'm not going to do this because I think you know how to do this, and we'll give you some in the homework, and it's tedious for me to just sit here and do it on the board for you. But you just look up, really just applying those laws of Boolean algebra. And it takes some cleverness. Like with any sort of optimization, you have to know the order to apply the laws. And sometimes you have to try different things to get it minimal. Asking the question, is a Boolean expression minimal? And by minimal, we mean fewer operators, fewer literals. Right? It's a difficult question to answer, is it minimal? Right? So you never really know if you're done. It's a simpler question to ask, are 2 things equivalent? So if I give you a form and another form and ask you to prove that they're equivalent, you know when you've proven it. If I give you an expression and say minimize it or simplify it, you never really know if you have it simple, right? Which is a little unsatisfactory, but you do the best you can. All right, so that was sum of products. There's the dual form, canonical form, which is the product of sums. And in this case, this is also called conjunctive normal form or max term expansion. So instead of min terms, we have max terms. And what these max terms are, these are places, these are terms that could cause the function to be 0 instead of the function to be 1. Right? So if A, B, and C are all 0, then this term is going to be a 0, right? A or B or C, right? If A, B, and C have these values, 0, 0, 1, then this term, because we complement the C, makes that all zeros, and that term's all 0. So here we're kind of in the products of sum form. What we're doing is enumerating all the places where the function could, all the ways that we can make the function be a 0, right? So that could make it a 0. If that's a 0, then we AND out everything, right? Else. If that's a 0, we AND out everything. We 0 out everything else because we're taking the AND of 0 with everything else, right? So this is the proper way to express all the different ways, these 3 things, where this function could be a 0, those 3 places. And then likewise for f bar, if we cared about it, there's 1, 2, 3, 4, 5 max terms here, and they're just ANDed together because it's the product of sums. Interesting to note here, the dual form of this canonic form, the product of sum form, the f function is more compact, and in the sum of products, the f prime function is more compact. Which is another idea. It says you could choose your canonic form based on, one being simpler. You could either do sum of products or products of sum if one's simpler than the other. Okay. And these are not minimal either, but I didn't reduce those. So you could do it on your own if you want. Okay, so that then answers the question, going back to this. How do we go from a truth table to a Boolean expression? If you have a truth table, I showed you how you make a Boolean expression. Once you have it in canonical form, then you can use some form of manipulation to simplify it. I'm going to show you another way to do it now that's actually simpler than this. Before we do that, I'm going to show you another example of applying the laws of Boolean algebra for doing simplification. We're going to go back to this adder example. So here's the truth table for one column of the adder, one cell in our ripple adder. The full adder cell has 2 outputs, R and C out. And if we look at this and write the canonical form for C out, which is here, we get this sum of products version is here. There's 4 min terms. So you have the and of 4 things, this one, this one, this one, and this one. And I think I have it right. This doesn't match what I showed you. What I showed you was the majority function, which was A, B, or B, C, or AC. If we were doing this the first time from scratch and we didn't know what the simplified form of this is, we could apply the theorems of Boolean algebra and we could simplify it. And I'm going to show you how you do that in this case because it's a good example. It's instructive. Okay, so we're going to start out with this canonic form, which we can write directly from the truth table. And this is kind of a tricky thing, but we're actually going to make things worse for a moment. I added one more term. In fact, I just duplicate that term, ABC. And we know we can do that because x or x is x, right? And we do this because you'll see in a minute why we do that. Okay, so that's the first step. And then I rearrange things. And we know we can rearrange things because it's commutative. So I move this second ABC term over here just to make it a little easier to see. And then I'm going to do this. Take those 2 things and I factor. Look here, we have A prime BC plus ABC. We can factor out the BC, and we're left with A prime or A times BC. Of course, A prime or A has to be a 1, right? Because either that's a 1 or that's a 1 in all cases. So we can replace that by 1. And so what we've done is reduced those 2 terms down to BC. It turns out really what this is just an application of one of those simplification theorems, but I spelled it out for you here without directly applying the theorem so you can see exactly how it works. Okay, so now you can see why we introduce this extra ABC term in here. And I'm going to do it one more time, and it becomes the fuel that we need in order to apply this simplification again. And then I bring it over here, and this time we have ABC and ABC prime. So we should be able to reduce that to AB. Actually, I went the other way. These 2. We've got AC, B prime, AC, B. So that we can reduce that to AC. Right? So that's AC. And then we do it one more time with the remaining 2 terms here. Factor out the C, the AB, and we're left with C prime or C, and then that reduces down. So this gives us our familiar form of the majority gate, which is AB or BC or AC. Now, anybody want to say anything? Yes? Sorry? Is it NP hard? Not for, I want to say not for 2-level logic for ands of ors or ors of ands. But if we have ands of ors of ands and ors, then it is NP hard. I'll have to find out. I can't remember. I don't think it is for 2-level logic. Okay. Yeah. Oh, so every circuit we've been talking about so far is 2 levels. You have ors of ands here. I'll give you an example back at when I showed you the adder. It's a good question. So this is 2 levels. You got 1 level ands, 1 level or. This is 3. You got we have or followed by ands followed by or, right?
Can you always reduce it down until?
You can always reduce it to 2 levels of logic, but and we'll talk about this later today. It might get much bigger. If you have common sub-expressions, you can kind of factor those out and then use that multiple places, perhaps, in your circuit.
So
and it introduces more levels, but it might be more compact.
So the greater than 2 level logic gate simplification would be NP hard because the expansion is like exponential?
Probably. I don't know how you prove that it's NP hard, but I know it. I'm pretty sure it is. Yeah. Yeah.
Is the NP hard problem statement like reducing it to 2 level logic if it's like n levels? Like what would?
Oh no, it's the finding the minimal.
Oh,
the minimal implementation would be the NP hard part. I need to check on the 2 level version though. Okay, but anyways, this is what we mean. So when we're writing an expression, what this relates to then, you can see in the expressions, you've got and, or, or, and or. It gives you multiple levels. So the 2 level ones always take this sum of products or product of sums. Not necessarily canonical, but sum of products or products of sum. Okay, so where were we? Yeah, so we did this. Okay, so the remaining topics. So I'm going to show you another method for 2-level logic simplification, which is much simpler than the algebraic method. It's kind of an old-fashioned method, doesn't get used much, but I think it gives us a lot of intuition about Boolean functions. And then, as promised, I'll say something about multi-level logic and why that can actually yield better results. And NAND and NOR networks, as I mentioned, they're interesting and important to us because in CMOS, NAND and NOR gates are much more efficient to implement than AND and OR gates. And then if we have time, my favorite function, exclusive OR, we'll talk about exclusive OR a little bit. Okay, so here's an algorithm for 2-level logic simplification. And the key tool we're going to use here is this theorem, the uniting theorem, which was one of the simplification theorems that I presented to you before. It says, and it's the one we used, by the way, a minute ago for simplifying the majority circuit. It says x times y bar or prime plus x times y is equal to x. Right? And I kind of proved it here similarly to the way I did in that simplification of majority. You factor out the x, and then you're left with y prime or y, which is a 1, and so that reduces down to x. So we can see that graphically if we look at a truth table of some function. Here's a function f, which I just made up. And if you look here at the changes in A and B and how the changes in A and B affect f, we get kind of a graphical version of that uniting theorem, because if A in these 2 rows, these are the 2 rows where the function is a 1. So when the function is a 1, you can move between those 2 values, or those 2 rows. A stays the same and B changes. If the output stays a 1, even though B changes, the output cannot be dependent on B. Right? That's really what it says. B goes from 0 to 1. It has no effect on f, therefore f is not a function of B, and we can get rid of B. And that's really all that this uniting theorem says here. So B changes in the onsets. We call the onsets the places where the function is a 1. A values don't change. So B can be eliminated and A remains. So this tells us that f is equal to A, really. Right? Likewise, here's another version, this function g. And we look, A goes from 0 to 1 here. B stays at a 0. Therefore, we can eliminate A because G can't be is not dependent on A. And in fact, G is dependent on the complement of B. All right, so G is B prime. Okay, so we can use that. Now we just need a more convenient way to visualize this, these so-called adjacencies, right? And this is what the Carnot map does, this Carnot map. So Carnot is the proper name for somebody who invented this. I don't know who or she was, but I think it was probably back in, 50 years ago or more. Probably much more than that, probably 70 years ago. Okay. What we do is we write the truth tables down in a different form. Instead of this tabular form before, we have this more graphical form where a function of two variables, A and B, can be written as a 2x2 little grid where these are the values A can take on, these are the values B take on. So this is the value of the function when A is 0 and B is 0. This is a function of we put in here the value of the function when A is a 1 and B is a 1, et cetera, et cetera. Now, if we want functions of more variables, we can use these, where here we can represent 0, 0, 0, 1, 1, 1, 1, 0 for all the values of A, B, and here's the values of C. If we want 4 variables, we can go up to 4. I'll show you when we have more variables in a minute, the way we do it. But here we enumerate all the different A-B combinations. Here's all the different A-C-D combinations. To make this work out easily, we use a gray code labeling here. And I don't know if people have heard of gray code before. Does anybody know what a gray code is? Okay, a gray code is a binary code where when you move from one combination to the next, you only change one of the bit positions at a time. So you can see here we go 0, 0, then we change the low bit to a 1, and then we change the high bit to a 1, and then we change the low bit to a 0. Using this principle, we can define gray codes for any number of bits. We just change one. We can move through all the different permutations, but we only change one column at a time. This is not a standard binary. If you think about counting in binary, we go all zeros, and then we have a 1, and then the ones are moving in a little at a time. Eventually, we get to all ones. The next step, we go to almost all zeros, except for a 1 in the high position. There we're changing lots of bits at once. Okay. We can talk later about the usefulness of gray codes, but this is one place to use gray codes because it helps make this easier, and it makes the whole technique work. Okay, so we have these ways of writing down these maps, which is a Carnot map is a way to write down the truth table. There's also 5 and 6 variable maps, which I'll show you in a few minutes if we have time. Now, once we have that, we can represent different functions. Just like we'd write the truth table for a function, we can write a Carnot map for a function. Here is this function f equals a. Right? When a is a 1, f is a 1. Everywhere else, it's a 0. Here's that other one we're looking at, g is equal to b prime. Says when b is a 0, then f is a 1, regardless of what a is. Here's this interesting function. It's f equals a. Here, we get the square shape thing inside the Carnot map because a is a 1 here and here. Doesn't matter what b is. Doesn't matter what c is. Right? And interestingly, here's our majority function here. You can see how simple it looks now. Here's the 3. So there's 3 things ORed together. C out is going to be a 1 if we get a 1 this way, or we get a 1 this way, or we get a 1 this way. The 1 this way is, well, C is a 1 and B is a 1. So that's CB. This one here, C is a 1 and A is a 1. So that's AC. And then this one here, A and B are both a 1, and C doesn't matter. Okay. So you can see there's a direct correspondence between these little groups inside the Carnot map and the Boolean expression. So the technique we have is you fill in the table as if it were a truth table. And then you look for these groupings, because the groupings tell us how to look at when the variables change and which ones we can eliminate and which ones we don't. For instance, here, if we were to put this function in here and we don't know what it is, we can see here, oh, when we move through all the values of the onset, A stays constant at a 1, B is variable, so therefore the function can't depend on B, and B is not part of the result. So it's kind of what I showed you in the truth table, and we can do it in 2 dimensions. So here's the technique. We draw the K-map of the appropriate number of variables between 2 and 6. We fill in the map with the function values from the truth table, and then you form groups of 1s. Right? Now, for this to work, the dimensions of the groups must be even powers of 2. So the group is that little circles that I've drawn, which group together the 1s. It could be 1 by 1, it could be 1 by 2, 1 by 4, 2 by 2, 2 by 4. Whatever it is, the dimensions of the group have to be powers of 2. You form as large as possible groups and as few groups as possible to cover all the 1s. So we're going to have to, at one point or another, cover all the 1s. Right? The fewer the groups, the fewer the fewer terms you're going to have in your final equation. Right? The larger the group and the fewer the groups, the simpler your equation you're going to have. Okay. Oh, you have to remember, the K-map is periodic in all dimensions. It has periodic boundary conditions. So if we look for adjacent, going back here again, this edge is adjacent to this edge. So this kind of map wraps around like this. If we had and this map kind of wraps around in both dimensions. We'll see more of that in a few minutes. Okay, and then for each group, write a product term. The term includes the constant variables, right? The variables that don't change when we move to all the 1s in that group. And then use the uncomplemented variable for a constant 1 and the complemented variable for the constant 0. Right? And then you form the Boolean expression as sum of products. So this gives us a way to directly write the minimized, simplified sum of products form. Here's a couple examples. So if I fill in the truth table, or if I have a truth table that has those 1s and 0s, I put it in this Carnot map. We know it's a function of 3 variables, A, B, and C. And then I can group together the 1s to cover. We have to group all the 1s one way or the other. So I can make a group of 1s there, and then this group of 1s, remember, it wraps around. Now, we could also make one here. That would just correspond to an extra term in here, and it doesn't add anything. We don't really need it, because that would be redundant. Once we cover all the 1s, we've covered all the 1s. This term here, C is constant, B changes, A is constant 1, so this is going to be AC. This group here, C is constant 0, and A is a constant 1, so that's going to be, A. Oh, this is wrong. Isn't that wrong? This is AC, and this one is C prime A, not B prime. Sorry about that. I don't know if I can correct this. Oh, I can't. It's a figure. I'll fix it later. Sorry about that. Here's another example. It's more complicated. What? Is it right? How can that be right? We're looking at this one here. So C0. Oh, it's these two. I was looking at these two. Oh, sorry. Never mind. I was stuck down here. Okay, yeah, if we go look here, those are the two 1s are. B is a constant 0, so it's B prime. A changes, so A is not included. Okay, sorry. Whew. Here's a more complicated function of 4 variables, A, B, C, and D. Remember grade code here, 0, 0, 0, 1, 1, 1, 1, 0. Periodic in 2 dimensions. So these 1s are all adjacent to one another, those 4 corners. The four corners is going to be D bar and B bar. That's this one here. This big group of ones, you can see the bigger the group, the more compact, smaller the product term is. This is going to be just C, right? Because A, B all vary here. C is constant here with a 1, so that's C. And then what's left is a single 1 here. Now, we could circle that 1. If we circled that 1 by itself, its term would have 4 variables in it. So we might as well capture this one, and we can reuse ones in multiple groups. And by capturing that one, it reduces this then term becomes A prime B D. Because we've eliminated, in the process of grouping in that one, we've eliminated C. So I just want to grab as many ones as possible together. Right. This may not be unique. There may be other ways to do this, but in this case, I think this is minimal. You can't get that one because they need to be power of 2 groups in order for this, the whole thing to work out. Yeah.
So you partition the 4 input literals this way to form the row and the column. Like A, B, C, D are the original are the inputs, and then you put C, D, A, B on. Like how do you know do A, B, and C, D versus A, B, C, D?
Oh, it doesn't really matter. I mean, I put AB on this axis and CD here. You could.
Well, could you put like 3 on one and 1 on the other?
3 doesn't. 3 doesn't. Well, if you did that, you'd have this long, thin thing.
Yeah, so
Then you would miss out on seeing some of the adjacencies. So you might be able to do it that way, but I don't think it would be really hard. So we usually make, in fact, I think you need powers of 2 number of rows and columns. In fact, it's either going to be 1 by 2 by 2, 2 by 4, 4 by 4. If you have more variables, then we're going to go to another dimension. Stack another one of these on top of this one. And then if you have another variable, 4 of them. Right? And then after that, I don't think that would be 6 variables. After that, I don't think this method works anymore. Yep.
Is it possible to have pathological cases where like maybe a long string is better? Like where like you could capture more together if you had a longer string?
No, as far as finding adjacencies, which is what this is all about, this is the optimal way to do it. Because you think about it, it's really a multi-dimensional cube. Can't explain it, but yeah, this is optimal. I'm sure of that. Okay, remaining few minutes. So that was so you end up, if you follow this technique, we're going to get a sum of products, right? Sum of products. There's the dual version of this, which is the product of some K-maps. In this one, you form groups of zeros instead of groups of ones. For each group, write a sum term. The term includes the constant variables. Here we use the uncomplemented variable for a constant 0 and a complemented variable for a constant 1. Okay, I'll show you what I mean by that. Here's some function here. Now, if you look at this function, it has a lot of 1s and very few zeros. So you would guess that maybe the sum of products form is going to be more compact than the product of sum forms. Because there's fewer zeros. So you're going to cover the zeros with less stuff. Right? I did it with 3 groups here. This group is going to lead to one of these. Here, look, C, D is constant 0. And then B is a constant 1. Constant 1 in this form, the product of sums, means B is going to appear as complemented. So we're going to have B bar or C, D. That's this one. And then this one right here is going to be C, D bar, A bar, which is here. And then that's the other one here that comes around. So it's the same technique. You just have to remember to turn the constant ones into complemented variables. And then here we're circling the zeros. So at this point, I wanted to do a large example where you could see this in action. I don't know how much time I'm going to have to do this today, but I'll just set it up and we can do it next time. Here's, we want to design this little circuit, a combinational logic circuit, that does a transformation from binary to binary coded decimal. And binary coded decimal is a representation where we represent decimal numbers where we use 4 bits per decimal number. Right, so if you have it, this used to be used in the old days of computing. When we're computing decimal numbers like dollars and cents. So if you had a number like 25, you'd represent the digit 2 as 0010 and the digit 5 as 0101. Right? So each digit would have its own 4 bits that represent it. What we do these days is we just take the equivalent binary number as from the decimal number and represent that way. But so this is coding the digits of decimal one at a time using 4 bits. And this is the way that coding works. Here's a map. If the decimal digit is 0 through 9, then we just use these binary numbers 0 through oh. This is not right. 0 should be 0. We're off by 1. This should be 9, 8, 7, 6, 5, 4. I will fix this for next time. What I want to point out here, though, is in this mapping, since there's only 10 decimal digits, we only need 10 out of the 16 possible inputs. So what we do, the idea of the circuit is we're going to put in these 4 bits, and what's, wait a minute. This doesn't make sense to me now either, because oh, it's an incrementer. Oh, jeez. It's not a converter, it's an incrementer. Okay, so, sorry. All right, so what I'm designing is a binary coded decimal incrementer. You put in a binary coded digit, binary coded decimal digit, and you get that digit plus 1 out. Okay, so if you put 0 in, you get 1 out. You put 1 in, you get 2 out. You put 9 in, which is this is the way you represent 9 in binary coded decimal. You get a 0 and then a carry. Right, that goes over to the next digit. But here all we're doing is the low digit. Just increment that. OK, so 4 bits in, 4 bits out, plus 1. Interesting thing here is that these values don't represent anything in binary coded decimal, right? But they're possible as inputs, right? But they probably will never show up. In fact, if the circuit is used in the context of some computing machine that's computing with binary coded decimal digits, these combinations of A, B, C, and D should never show up. Therefore, in our truth table here, which is what this is, you can think of one column, each column as a function here, I put a dash because that's saying don't care. We don't care what the circuit generates in that case because that value should never, this value should never be seen at the input. So we're going to let the circuit do whatever it wants. And we can use that don't care condition to help us simplify the circuit. And just a little preview, when we make our Carnot maps for these 4 functions, we put these dashes in the Carnot map, and we can make that dash be a 1 or a 0, whichever one makes our circuit simpler, right? gives us bigger groups of one, or gives us opportunity to group more ones together, right? So that's kind of the key here, is we can use these don't care conditions to help us simplify the circuit. And we'll do that on next week. So have a good weekend. Remember, the homework is due on Monday. So, and go to the discussion tomorrow if you need some help.